This video will be focusing on what's referred to as the natural base. The first thing I want to do is just go over something that you've discussed with me already. Numbers 1 through 3, what we're going to do here is simplify. Starting with number 1, we have a common logarithm. Remember, when they don't specify a base, it's understood to be 10. And when we have the base of our logarithm matching the base of the exponent, they undo one another, or they essentially cancel out, and we're just left with the exponent. So the answer here would be x. Same thing with number 2. The base of the logarithm matches the base of the exponent. It doesn't matter that they're not numbers, they're variables. They're still the same, so they still cancel out, and we're just left with the exponent, 3w. Once again, we have a common logarithm. Just this time, it's an exponent that has a log in the power, but it doesn't matter if they're switched or not. The bases are still the same, so they still undo one another, making the answer z. What we've exhibited here is inverse relationships. They're opposites of one another. The natural base is actually just a number. It's very similar to pi. We know that pi represents a number. It's 3.14 and then continues forever. The natural base e I actually have over here. I'm just going to scooch over the camera a little bit. The natural base e is 2.718, and then it's just going to keep going and going and going. So if you're ever going to use an approximation, the more places you go, the more accurate your final answer will be. But again, it's just going to be an approximation. Okay. It says, recall the natural base e has an inverse relationship to the natural logarithm. So we've actually seen in a previous video that we denote the natural logarithm as ln. And if ln and the natural base e are inverses, that means they undo each other. The way that we would simplify the natural base is actually the same way we would simplify any exponential equation. So we still use the properties of exponents. For part A, we have e cubed times e to the 4th power. Remember, whenever we multiply two things that have the same base, we add the exponents. So this is equal to e raised to the 3 plus 4 power, or e to the 7th power. When we divide, we would subtract the powers. So the first thing I would do is do 3 minus 2, which was 1, so I have e to the 1st power. But also, don't forget those constants. 10 divided by 5 is 2, so we have 2e. C, there's a couple of different things here. The first thing is this whole expression is being raised to the 2nd power. Whenever you multiply two different things together and it's raised to a power, you need to distribute that power to both terms. Then this becomes a power to a power property where you need to multiply the powers together. So I have a 3 to the 1 times 2 power, and then e to the negative 4x times 2 power. So that's 3 squared, or 9. And that's e to the negative 4 times 2 is 8x. This is not an acceptable answer, though. We talked about how whenever we have negative exponents, we need to move it. I'm going to make a note of that because a lot of you made mistakes there. So negative exponents, we move. That means we need to move the e to the 8x down to the denominator. So we now have 9 in the numerator because 9 is to the 1st power. It's a positive exponent, so that stays. And then e to the 8x has been moved to the denominator. The act of moving it has now made the power positive. So that's our final answer. For part D, we have the natural log of e to the negative 2t power. This actually is just like the problems we did in the warm-up, so numbers 1 through 3, where the base of the logarithm matched the base of the exponent. So here, the natural log, remember, is equivalent to log base e. So my base of the logarithm does match the base of the exponent. That means they cancel out, and I'm just left with that negative 2t as my final answer. For e, we do have e and natural log again, but we do have a bit of a problem. They're not right next to one another, so they can't cancel out right away. The only way to take care of this is if we move that 5. And we're actually going to do the other direction of the power property. So sometimes, remember in the notes, if we had a power here, we would move it out front. Well, we could also move a number that's in front of the logarithm and put it back as a power. So really, I can rewrite this as e to the natural log of x to the 5th power. Now that they're right next to one another, I can cancel them out, meaning that the answer is x to the 5th power. Okay. All right. For f, we just have natural log and e, so they do cancel each other out. We do need to write something as our answer, though. That something would be 1, and I want to show you why. Remember, the natural log is equivalent to log base e. So I have log base e of e. And I showed you something called circle trick before, which says we start here and ask ourselves e to what power will give me e. So e to what power would give me e? Well, that's e to the 1st power. So that's why the answer is 1. Part G, they're already right next to one another and they're inverses, so they cancel out, and we're just left with x minus y. For h, though, they are not right next to one another, so I'd have to rewrite it as e to the natural log of x cubed, because I use power property to bring that back up there. I can cancel. The final answer is x cubed. I, we have e to the 5th power times e to the negative 2. There's a couple different ways that you can approach this. You could either go ahead and add these two together because we're multiplying. So 5 plus negative 2 gives me e cubed. So I added here, or you could take care of the negative exponent. So I say, okay, well, that means I need to move it down to the denominator, so e squared's down here. And then you'll see this becomes a quotient property, which is where we subtract. But still, you'll see we get e cubed. So it just depends on how you see that one. And J, I just want to remind you that these are two separate things. We have a 2 to the 1st power, it's a constant, and then we have e squared. So two separate things being raised to a power, we would need to distribute that power to both terms, which makes a power to a power rule. So I have 2 cubed, and then e to the 2 times 3 power. Remember, when something's cubed, you multiply that something by itself 3 times. So 2 times 2 times 2, which is 8. And then e to the 2 times 3 is 6. So 8 e to the 6th power is the final answer. All right, next, I just want you to practice plugging it into your calculator. So if you have a TI-30X, I just wanted to show you that you would hit second natural log, and you'll get e to the power of, and then you just type it in. So e to the power of 2 is part A of example 2. That's approximately, let's go Let's go 2 decimal places because I have seen some rounding mistakes. If I want to round 2 decimal places, so this is a hundredths place, I have 7.38. But the number after the 8 is a 9. So if it's 5 or greater, we're supposed to round that number up. You should put approximately 7.39. Okay. Part B, we have e, so I'm going to hit second natural log to the negative 0.06. So we don't have to move it down to the denominator. We can go ahead and just plug in that negative exponent and hit enter. Let's go 2 places once again. Just as a reminder, I need to look at the third number to see if I round up or not. So I have 0.94 and there is a 1, so I don't have to round that 4 up. It just stays approximately 0.94. Had I gone 3 decimal places, that would be 0.942 because the 7 would have boosted up that 1. All right, now we're going to take a look at example 3, which is solving logarithms. Before we can solve, we want to make sure we have it down to 1 logarithm. So we may have to condense if we have more. Like in example A, I'm going to have to condense this. Remember, we talked about product property, quotient property, and power property. So I'm just going to review those as I go along. When I look here at example A, I have natural log of 5 plus the natural log of x equals 1. Even though it's a natural log instead of a regular logarithm, the rules still are the same. Because it's addition, I need to multiply these 2 things together. It's the natural logarithm of 5 times x equals 1. Then in order to solve, I need to get x by itself. I don't have the logarithm on both sides, so I'm just going to have to undo the logarithm here. And to undo a logarithm, I'd have to exponentiate each side. So again, this should seem familiar. Remember, the base of the exponent needs to be the same as the base of the logarithm, which we know is e. So this would cancel out, leaving me with 5x here, and then I would have e to the first power on the other side. So 5x equals e to the first power. X still isn't by itself. I need to divide each side by 5, so x equals e over 5. This is your exact answer, and I'm fine with you leaving it this way. If you wanted to plug it into your calculator, it would look like this. You'd have to put e to the first power divided by 5. Let's say I want to go 2 places. I'm just going to continue that. It's going to be 0.54. Notice how with my exact answer, I put an equal sign. With my approximation, I used approximation notation. Let's take a look at example B. So B here I have subtraction, which means now we're going to use the quotient property. The 5 needs to be in the numerator, the x in the denominator. To undo the natural logarithm, once again, we're going to exponentiate each side. This cancels. I have 5 over x equals e cubed. And I need to get x by itself. Well, it's currently stuck in the denominator, so let's multiply each side by x to get it out of the denominator position, leaving me with 5 equals e cubed x. Remember, e to some power is just a number, so treat it like any other number. Whenever we multiply x by a number, we get rid of it by dividing. So my exact answer is 5 over e cubed. But if I want to write an approximation for that, I'd plug it in, 5 divided by e, oops, hit the wrong one, 5 divided by e cubed. I get approximately 0.25.